how do we do filtering circuit, right? As we have already seen on our previous modules, previous things, we know how to make use of an operational amplifier and what are the advantages and disadvantages of going with an active filters when compared to the passive filters, and we have also discussed about the design. Just recall what we have discussed, and if I see here, this is our active low pass filter, right. So, the combination of R and C tells our cutoff frequency, and the combination of R1 and R2 resistors tells us gain. Now, what value of cutoff frequency we require? We require a cutoff frequency of 100 hertz. Since it is a low pass filter, I do not want to see odd multiples of our power line interference, that means 150 hertz, 300 hertz, everything. So, we will be using low pass filter with a cutoff frequency of 100 hertz. Now, how do we know the cutoff frequency? So, in this case, we are considering a resistance as 670 kilo ohms. This is R1 670 as well as R2 also as 670 kilo ohms. We are taking 670 kilo, this is also at 670 kilo, and capacitor as 2.2 nanofarads. Now, if I can compute the cutoff frequency, what is the formula? Fc is equal to 1 by 2 pi Rc, right. So, when we calculate everything, we will get a cutoff frequency somewhere around close to 108 hertz. If I take 2 nanofarads, it will be even 120 hertz, we can even get it, or if I take a smaller value, it will be 100 hertz too. I mean, if I take a larger value, it will be either resistance or capacitance, it will be even 100 hertz we can achieve. So, in this case, by considering the availability of resistors and capacitors, we are designing a first order low pass filter with a cutoff frequency of 108 hertz. Then what about the gain of the system? Since R1 and R2 resistors are same, since it is an inverting amplifier, the gain is R2 by R1. So, therefore, the gain is 1 in this case. So, what are the input we get? Without any amplification, with an amplification factor of 1, we will get the same output, but since it is an inverting, we will get a negative. There will be an off phase shift of 180 degree. Now, how do we know? Since see, if I want to understand the circuit, I should look whether it is cutting off at that particular frequency. I have to have a frequency spectrum, and connecting it to a frequency spectrum will be very expensive too, because the equipment itself is very expensive. So, what we can do is that if I can visualize whether the designed filter is cutting off at that particular frequency in a CRO itself, we can even compute the same thing in our laboratory too. How do we do that? So, as we know that when we look into the frequency spectrum of low pass filter and the gain is 1. So, if we can calculate the 3 dB line, right, this is nothing but our cutoff frequency. Now, when I represent in a frequency form, we are saying this value is 108 hertz, but in CRO, how do we found it? What we do is that we know what is the maximum voltage we get, right. So, we will apply some we will take some function generator, we will apply 1 volt as an input signal. So, since it is also a gain of 1, we will get an output as 1 volt. Now, we will slowly increase the frequency, and we will observe what is the change in the amplitude. Whenever we see 3 dB line, which is nothing but half input voltage or 0.70 times that of your input signal, that particular at that particular point, that is nothing but our 3 dB line, and from that point the output voltage will be keep on decreasing. So, that frequency if I can calculate, that is nothing but our cutoff frequency. But to give the frequency domain visualization, what I will do is that in a simulation I will show you the AC response as well as with a DC response, and we can see the complete the frequency domain value too. But this is how the connection should be looks like, and we will be using a function generator to pass from 1 hertz to somewhere around 200 hertz within steps of 20 hertz, and we will record the output at each frequency. So, we will observe the signal generator frequency for which the output is 0.707 times lower than the input signal. That point is nothing but a 3 dB point. So, that point we will consider as our cutoff frequency. So, in order to understand much more, what we do is that we will go to multisim. So, as we have already seen how a multisim looks like and everything in even our previous module, but our intention here is to design a filter and we see the frequency response as well as whatever the intuitive that we have learned from the experiment from the previous experiments as well as the in our procedure that we explain, we will try to put the same thing here and we will try to analyze even in a time domain too, and we will compare the frequency domain response with the time domain too. So, in such case what I need now, first I have to take my operational amplifier. So, I will go to op amp and I will select an op amp here, right. Then I have to take resistors. In this case we have taken 670 ohms resistor. So, I am replacing with 670 kilo ohms, sorry 670 kilo ohms resistor, and one more resistor that is also 670 kilo ohms. So, that is a negative feedback resistor. So, I will be connecting from here to here. Then what is the other one? So, we also have to connect a capacitor across R2. So, what I will do? I will take a capacitor. What is a capacitor that we have used in our theoretical designs? We have used 2.2 nanofarads. So, I will go with the 2.2 nanofarads, 2.2 nanofarads, and 2.2 nanofarads are available in the market too, right. Then this particular value should the positive terminal should be connected to ground. So, what I will do is that rather than connecting to ground, in order to eliminate the effects due to the bias and offset currents, I will use a resistance value, two resistors in parallel which are nothing but 670 kilo ohms resistors itself. So, that the effect due to the bias and offset resistance can be completely removed using this, right, that we have already studied in our previous modules, is not it. So, I am taking R1 and R2 resistor and these two we are connecting it in parallel. So, that it will compensate for the effects due to the bias currents as well as the basically for the bias currents. Then I have to apply some AC voltage, right, and the other terminal should be connected to ground. I will take it to ground. This is my input. So, in order to visualize the system, I will take here input, other one I will take output. Now, so in order to understand the cutoff frequency, good way is to go with our AC sweep. So, what I will do is that in AC sweep, I will sweep the signal from, okay, let it simulate, yeah. So, here what I will do is that the minimum hertz is of 1 hertz I am doing and the maximum, say I will go with 200 hertz, right. Then we may not require the peak values, sorry phase values. So, I will remove all the phase values, I only put magnitude values or even greater than minimum 0 and maximum somewhere around 1000 hertz I will put, or 1 hertz to 1000 hertz, right. Let me run once again AC sweep, okay. Phase I am removing it, then till 1 mega I will put 1 mega. So, now we can see the signal 1 mega, right. Now, green represents what? When we look into our figure, we can see here green is nothing but my input and blue is nothing but output. So, one thing is clear that the input and output are having the same gain, right, amplitude of 1, right, magnitude of 1. So, that means both are having the same gain, but after particular frequency, if I closely observe, the output is attenuating, right, the magnitude is decreasing, right, but at what frequency? How do we calculate our cutoff frequency? As we know that the 3 dB line, we have to consider the 3 dB line, since it is 1, 3 dB line will be 3 magnitudes below to the 1. So, in order to do that, what I will do is that I will zoom the frequency domain. So, in order to do that, I will change this frequency values to somewhere around 1 kilohertz. Now, this is 1 dB, the below one is 1 dB, this is other dB and this is this dB. So, this frequency, right, somewhere around 700, right, this is 1 and this is 700. So, approximately 3 dB line. So, when I see that what is the frequency at this point, we can see here 100 hertz comma 733.68 milli dB, or if I put a cursor, I will put x axis cursor. So, I will be slowly varying, observe the C2 cursor, I will be varying it to 99, sorry, where is that, 3 dB line. So, the C2 value should be, so let us take somewhere around 100 hertz, then I will take y axis cursor. So, because we require to take 700 milli magnitude. So, slowly I am increasing, observe dy delta y here. So, this particular value, right. So, 750, 800 slowly decrease 694. So, this is nothing but my line. So, this is my, if I observe this point will be, this particular point will be 700 milli, somewhere close to this. I am unable to do that because of the resolution. Okay, 1 kilohertz. Because of the resolution, I cannot see that, or also I can little bit zoom the vertical scale. So, maximum minimum I will say somewhere around 1 milli, right. Now, if I see 125. So, we can understand that somewhere close to 100 hertz, right. Now, how do we do the same thing, how do we understand when we look into, when we are looking into CRO. So, in order to understand, what we do is that rather than going with AC sweep, I will go with interactive. So, here starting from 1 hertz will change and we will observe the input and output frequencies. So, I will increase the time division, I am increasing time division. So, we can see that we can easily observe the phase difference. So, I will make it auto. We can see the phase difference, this is our input, the green color one, the blue color one is nothing but our output. Because of we are using inverting, there is a gain phase difference, and the amplitude wise it is one and the same. Now, I will slowly increase the frequency, there is no change in our gain. So, with the rate of 20 hertz, so I will go with the 20, I will make it as single or auto, and in order to visualize I will decrease the time division, right. Then again I will go with the 40, right. So, in order to understand that, let me put a cursors. So, what I will do is that I will go with the cursors and make it as an y axis cursor. So, at what point we have to see? We have to see a point at 0.707. So, I will put the cursor one at 707 millivolts. So, we can see right now the cursor, yes. So, cursor 1 is at 70, whenever this blue color line is below the 707, that frequency is nothing but our cutoff frequency, right. So, I will increase. So, I will increase to 50, no, not decreased yet. So, I will go with 60, no change, not lesser than 707 millivolts, 80, not even. So, I am going with 100, right, almost close. Now, we will increase one by one. So, before going that, what I will do is that a little bit time divisions I will increase it, so that easy to view, increase, right, somewhere around close to 105, almost coming close. Now, I will increase to 107, right, even little bit higher. So, I will go with 108, right. If I see that, if the input is at 108 hertz, the output voltage is 707.55 millivolt. Even if I increase it 109, right, 1010 started slowly decreasing it, 120 decreased. So, that particular value is nothing but our cutoff frequency. So, in order to visualize by using a time domain signal by looking into CRO, one way to do is slowly increase your input frequency whenever it goes to the 3 dB line, which is nothing but 0.707 volts to that of your 70% of your maximum voltage, that is nothing but 707 millivolts. Whenever the input voltage is lower than 707 or just at that point of 707 millivolts, that frequency is nothing but our cutoff frequency. So, we have seen that it is nothing but somewhere around 108 hertz, right. But even though if I increase the frequency, it is not suddenly attenuating it to even below than 500 milli. The reason is the rolling factor. The roll off factor of first order filter is 20 dB per decade. Because of very smaller rolling factor, it will also allow particular band of frequency to pass through, but we require a cutoff. We do not have to pass a frequency at 150, that is what our power line odd multiple frequency. But since roll off factor can be if I observe at 150 hertz, we can see that, right, only it is even much more below than our cutoff frequency. So, we do not have any problem. Now, we will simulate, we have done the simulation, we will do experimentally the same thing. Since we do not have a frequency spectrum, we will show you how to do the same analysis in our using our breadboard, and we use a function generator as well as an oscilloscope, and we visualize the same thing, and we will observe at what particular frequency it is reaching to 707 millivolts. When we look into the breadboard, this is a complete signal conditioning as well as a processing circuit that we are going to use in this particular case study. So, if we observe here, this part is our instrumentational amplifier part. This part contains low pass filter. If I see, I am using 2 nanofarad. This is our 2 nanofarad, the green color wire. Here we can see, this green color, this capacitor is a 2 nanofarad 2.2 nanofarad capacitor, and these are our 2 resistors, one is here, other one is here, 670 kilo ohms, right. This is a TL082 IC. So, it has a dual op amp. One side of op amp we are using low pass filtering. Now, we will see this low pass filtering circuit, how it works, right, and the connections I have already discussed in the simulation as well as even in our PowerPoint too. So, the same circuit I have made it on a breadboard, and we will apply an input from the function generator, right, and we will observe the output in our oscilloscope. So, how do we do that? So, first thing, since it is an active filter, we have to power it. So, we will take a voltage source, we will connect plus 15 and minus 15 to our breadboard. So, now what we are doing is, onto this particular part, wherever we have designed a filter, low pass filter, which is similar to that are the experiment that the connection that we have seen in our simulation as well as our presentation, we can see one side of an operational amplifier is a low pass filter. So, now by using a function generator, it is being connected to the input resistor. So, here we can see this input resistor, to this input resistor we have connected this white color wire, right. So, from one side of operation CRO oscilloscope, we use a wires and we will connect it to the same point, so that we can see the input signal too. So, here I am connecting it to oscilloscope 2. This is the input to oscilloscope. Input signal is giving connected as an input to the oscilloscope, and ground to ground. Then what is other one? We also have to see the output. So, another probe, we are taking another probe of oscilloscope and connecting it to the output. So, output here is 7th pin, right. So, 7th pin is this one, and this is to ground. So, what we have done here, from our voltage supply we have connected plus 15 and minus 15 to their respective inputs provided on the breadboard. So, that here by using wires we have already connected to the all the ICs. Whenever I switch on, the all the ICs whichever used on the breadboard will be powered with a plus 15 and minus 15. Okay. Then from the function generator, using the function generator we will generate different frequency input sinusoidal frequency signals starting from 1 hertz up to more than 100 hertz. So, that we can observe at what frequency the input is becoming 707 millivolts, right. So, 0.707 volts. So, that is being connected as an input to the system, to the low pass filter. So, at the point of input resistance which is nothing but a R1 resistance, and output is taking it 7th pin of op amp. This is since it is a TL082. So, we are using the second op amp of TL082. So, the output is at the 7th pin. So, we have connected to the 7th pin. Now, I will switch on the power supply. Okay. We switch on the power supply and make it as auto scale. Switch on function generator. Increase the scale. So, the input voltage applied is so here we have to change the input voltage. So, the amplitude I am going to the amplitude setting it as 1 volt and offset I will make it as 0, offset as 0 volts, right. So, we can see. So, rather than taking this, what I will do is that 1 volt to peak 2 volts peak to peak we will apply. So, we will go to high amplitude to 2 volts peak to peak. So, we can see 1 volt input as well as 1 volt output. Now, to visualize the signal, so I will just increase the scale to 1 volt both the input as well as an output and make it at single point. So, I am shifting the both signals to one point, that is 0 position. So, yes 0 division, and we have an offset of 500 milli. Even I have to remove the offset here. So, I will go to offset, make it 0 volts. Now, there is no offset, we can see that. Now, slightly increase the scale, right. So, yellow represents our input signal, right, and the blue one, the second one is our output signal. When we observe, there is an phase difference between the input and output. This is because of our inverting amplifier. So, we know that inverting amplifier will have a 180 degree phase shift because of that. Now, but what about the amplitude? We have to look about the amplitude now, isn't it? So, what is the voltage below which we have to consider? What is the voltage that we have to consider to calculate our cutoff frequency? 707 millivolts. So, what I do is that in order to understand, I will create a cursor and I will create amplitude cursor, right. So, I will put the cursor at 707 milli. So, since we have even more range, what I will do is that I will increase, I will decrease the width of it. So, I am making it as 500 milli as one block, even for the negative to 500 milli. Now, by using a I will change the division 0. So, one division now it is equal to 500 millivolts for both input as well as output too. I will go with a cursor, I will put it at 707 millivolts. So, I will go to cursor 1, right now it is at 180 milli, I will go slowly, I will go till 707 millivolt, 520, 580, yes 700 millivolts. So, I will observe by changing the frequency, input frequency, we will see at what particular frequency the output voltage is below that particular threshold that we have set, right. The threshold is 707. Now, we will slowly change the frequency at an interval of 20 hertz. So, when we look into the function generator, right. When we look into the function generator, I will go to the frequency and I will change it to 20 hertz. Right now it is at 10 hertz. Observe the input and output. I am changing the knob there. Now when I see the output, still the amplitude is still following, right. It is even greater than the line. That means this is not our cutoff frequency. Now I will change it to 20, going here, going it to 20. What is the frequency we are getting? Right. Observe the frequency. Frequency is same, amplitude even above the threshold value. So that means even this is not. I will increase to 30, 40 in this case. I will go to 40. Observe the output. Right. Even more. Even more. Right. Now go to 60, 40, 50 and 60. Observe, same. So even that is not our cutoff frequency. Then 80, 80, even observe it is even greater than the threshold value. So the threshold is at 700 milli, right. Then again I am going to 100, right. When I look into the oscilloscope, I can see that very close to the cutoff, very close to our 3 dB line, right, very close to the 3 dB line, which means that this is our almost near to our 3 dB line. So I will slowly increase the input frequency and we will see at what point it is started decreasing it. So to visualize it, I will increase, I will change the scale. So we can see 102, 103, 4, 5, 6, 7, 8. Now if I clearly observe here, when we zoom into this particular point, at this point it is slightly below than that of our threshold value. This threshold is 700 millivolts, right. So but if it is greater than this value, we can see the value is slowly decreasing. That means the output is attenuating, right. We can observe that value is slowly decreasing, the amplitude, the output, see we can observe that only the output amplitude is decreasing. Now when we recall our filters, we know that the output will not remove, the output will be attenuated above the cut for a low pass filter, above the threshold frequency, above the cutoff frequency, the output will not be removed, it will be attenuated. So here we can see higher the frequency, the amplitude of the output is slowly decreasing. So from this experiment we can conclude that the cutoff frequency of the filter is somewhere close to 108 hertz, right. Even with our theoretical design we got 108 hertz, even with our simulation design we got 108 hertz. So this particular filter, this particular operational amplifier, this particular circuit, we will use this for our low pass filter circuit. So that the power line interference due to odd multiples will be completely removed by using this low pass filter. Now what next? We also require to have notch filter as well as high pass filter. Now we will look into the high pass filter circuit, right. We will look into the high pass filter. So when we go to the presentation,